You can find the Fourier series for the periodic signal only. Therefore, you must know how to differentiate a signal whether it's a periodic signal or non-periodic. In this case, the signal repeats itself after 2 pi. So 2 pi is the fundamental period. So it repeats itself from negative infinity to infinity. Therefore, this is a periodic signal with the period equal to 2 pi. So this is yes, and the period is 2 pi. Next, you need to find the function for this periodic signal. You must write the function fx within one period. For example, from here to here is one period, or from here to here is one period. So if you choose this period, then we can write the function to be -1 from -pi to 0 here, and the function is 1 when the x is equal to 0 to pi. So if you only write this formula without this, then when you draw this, you have 1 when it's equal to 0 to pi, which is here, and -pi to 0, you have -1, which is here. So you see, this signal is only one cycle and it's not continuous. It's not repeat from negative infinity to infinity. Therefore, this is not periodic signal. To make it repeat over the time from negative infinity to infinity here, you must include this formula. So this formula says that the function fx will repeat itself for every 2 pi period. If you want to draw a periodic signal like this, where you have a rectangular function from negative infinity to infinity, it's difficult for you to use this function to draw it because this function is only valid for one cycle. One of the applications of the Fourier series is to plot the periodic function. After you find the Fourier series for this periodic function, then you should obtain this. So this is the Fourier series result that you obtained from the rectangular signal previously. You know that the periodic function fx is equal to the summation of multiple terms here. So if you take the first term and assume that fx is approximate to this function, then fx is approximate to x1, where the x1 means the partial summation of the first term. So if you plot it, you obtain a sine wave, and sine wave is not a good approximation because it's not similar to the rectangular wave. Let's include more terms for the approximation. Let's take 2 terms here, so you obtain the partial summation x2, which is this, and if you plot it, you obtain this curve. So this curve is also a poor approximation. So you see the partial summation is an approximation to the fx. The more term that you take, the approximation to the desired rectangular wave will be improved as well. As a rule of thumb, we can use the partial summation of 20 terms to give a good approximation. For example, let's say you take the partial summation of 20 terms, where you take the first term, add with the second term, third term, and so on until the 20 term. This is the result. And this result is approximate to the function that we want. If you want to obtain higher accuracy, then you should increase the number of terms. For example, you can choose 100 or 1000 terms to plot the rectangular function here. In this question, we want to know what is the frequency contained in this rectangular wave. From the graph, we know that the period is equal to 2 pi. Therefore, your omega is equal to 2 pi divided by p, and you obtain the omega equal to 1. This is called the fundamental angular frequency. If you only have one frequency in the signal, then you will obtain a sinusoidal function like this. However, this graph is not a sinusoidal function. Therefore, this function must contain other frequency. So how can we find the remaining frequency contained in the rectangular wave beside the fundamental frequency here? One of a way to find the frequency of a periodic function is to perform the Fourier series, and this is the Fourier series result. By using the Fourier series, you success to decompose the periodic function, which is the fx, into the summation of multiple sinusoidal waves here with various frequency. The lowest frequency that you obtain is equal to 1, so this is the fundamental angular frequency. The remaining frequency that you find, such as frequency equal to 3, 5, 7, and so on until infinity, so this is the harmonic frequency. Therefore, by using the Fourier series approach, you success to decompose the periodic function and obtain the frequency information inside. To be 1, 3, 5, 7, 9, 11, and so on in radian per second. You see, it's impossible for you to review this frequency information in the original function here. So Fourier series is very useful to review the frequency information inside the periodic function. In this elimination, partial summation of x4, which is taking the summation of these 4 terms, is approximate better to the rectangular wave compared to x1, x2, and x3. For the first term, you see the rotation is moves slow compared to the 4th term here. This is because the frequency of the first term is lower compared to the 4th term here. So omega for the first term is 1 and the frequency f is equal to 0.16 Hz, which means it rotates 0.16 cycle per second. Where omega equal to 7, the frequency is 0.7 Hz, which means 0.7 cycle per second. The amplitude of the first term is larger than the second term, followed by third term and fourth term. You can obtain the amplitude information from here. So this 4 over pi is the amplitude for the first term. 4 over 3 pi is smaller than 4 over pi, which is the amplitude for the second term here. 4 over 5 pi is the amplitude for the third term here. And lastly, you have 4 over 7 pi, which is the smallest amplitude among these 4 terms. Therefore, it has the smallest circle. This is the graphical representation of what we are doing so far. Initially, you have a rectangular wave for fx versus x. After you perform the Fourier series, you obtain the result in multiple sinusoidal waves with corresponding frequency and amplitude. So if you plot the amplitude versus the frequency graph here, you will see for the first term, you have the amplitude 4 over pi and the omega 1 radian per second. For the second term, you have smaller amplitude, which is 4 over 3 pi, and the frequency increased to 3 radian per second. If you continue the same procedure, you obtain the amplitude for the third term to be 4 over 5 pi here, and then the frequency is 5. Lastly, at frequency 7, you have the amplitude 4 over 7 pi here, and so on. If you look at this domain, which is the amplitude versus the frequency, you obtain the frequency domain. And this tells the frequency contained inside this rectangular wave, which is 1, 3, 5, 7, and so on until infinity. So these are the frequencies. If you wonder why you get one line here at omega equal to 1, look at this sinusoidal function. So the amplitude for this sinusoidal function is from the 0 to the peak. Therefore, if you look at this view, you see there is only one line which indicates the amplitude here. You can draw the sinusoidal function here from this term. This is the first sinusoidal. Second term here is the sinusoidal function 2, which is appear here. Repeat the same procedure, you can obtain the sinusoidal function 3, 4, 5, and 6 here. If you look at this view, then this function here is equal to the summation of the sinusoidal function 1 until 6, which is the partial summation x6. So if you look at this is approximation to our rectangular wave here.
The third application for the Fourier series is to obtain the final result of a series. You have an infinite series here. You want to know what is the summation result for this. In fact, this can be obtained from the Fourier series result that we obtained previously. When your x is equal to pi over 2 here, substitute the x to pi over 2. On the left hand side, the function pi over 2 is k. Substitute the x to be pi over 2 and compute the sine. Then you obtain sine pi over 2 equal to 1, sine 3 pi over 2 equal to negative 1, and so on. You take the 4k over pi from this equation, and then you obtain the 1, negative 1 over 3, 1 over 5, negative 1 over 7, and so on. To obtain the answer for this series, let's move this to the right hand side. Then you should obtain pi over 4 on your right hand side where the k can be cancelled. Then you obtain the answer for this series. This is called the Leibniz series, where it can be simplified into this term. So when you substitute n equal to 0 inside, negative 1 over 0 is 1, divided by 0 plus 1, you still obtain 1, which is this term. When n increases to 1, substitute inside, you obtain negative 1 divided by 2 plus 1, which is negative 1 over 3. And if you continue, you should obtain this. Previously, you learned about several types of series, such as the geometric series, exponential series, cosine series, and sine series. Leibniz is the first guy who found the infinite series for pi. So from this formula, you can obtain the pi to be this answer.